different y values, right? So the vertical line test, all that fun stuff, right? You guys remember that from algebra? I'm sure you'll review. So functions. So remember, kind of no repetition in the x type of deal. No repetition in the x, the vertical line test. Now, we know the function notation. F of x equals some algebraic expression. And we can, of course, evaluate functions using this function notation. For example, if f of x equals 3x squared minus 4x plus 1, then f of negative 1, how do I do that? Yeah, plug negative 1 for x, so 3 times negative 1 squared minus 4 times negative 1 plus 1 equals something, I don't care. Right? So again, the function notation works. Whatever I put in the little parentheses ends up replacing the independent variable, right? So if I ask you what is f of t minus 7, you will say it is 3 times t minus 7 squared minus 4 times t minus 7 plus 1. Whatever that equals to, I can open up the parentheses and so forth. And of course, all of you seen me do my favorite example with a function. No. Yeah, that one. Right? So it's smiley face is going to happen there twice. So we have equals 3 smiley squared minus 4 smileys plus 1. Right? So whatever goes in the parentheses ends up replacing the independent variable. So when we're dealing with functions, one big thing that we need to talk about is the domain. So domain. So when we talk domain, we mean what? If I ask you find domain of the function, for example, f of x equals square root of 4 minus 3x. Basically, I'm asking you find the set of all real numbers. So the values of the function are real, right? So that means no division by 0, because if you divide by 0, you technically get an infinite value, which is not a real number, or you get a square root of a negative, which is not a real number. So when you're dealing with square roots, who remembers how you find a domain of a square root function? What do you do? Well, no. Greater than or equal to 0. What do you set to greater than or equal to 0? Yeah, so you take the radicand, wherever's under the square root. You want to make sure that the radicand stays non-negative. So then the solution to that inequality will be the domain. Now, the way you solve your inequalities is solely up to you. Subtract 4 from both sides, right? And then divide by negative 3. Now, what do we need to remember when we're dividing by negative 3? What? Yeah. So reverse the sign. So x is less than or equal to 4/3. Right? So we can express this in the interval notation. So that's from negative infinity to 4/3, including 4/3. Here is set notation. It is all x's, so that x is less than or equal to 4/3. right? It's a fancy set notation, set builder notation. We can graph the solution. So, if this is 4/3, so we are everything to the left of 4/3. We use a brackets. Now that's kind of a new thing. And my math lab uses a bracket instead of a dot and a circle. But if you use a dot or a circle, I'm totally cool with that. If you're as old as I am. Right? Happy? Arthur? Well, because again, you're solving for just one variable, so it's a kind of a one-dimensional entity. So it's only considering a number line. Okay, you're not doing if I had a function, a three-dimensional function where domain consists where x and y independent variable, then the domain will be some kind of a blob on the xy plane. So then we'll have a more of a graph. What? Yeah, it is. Well, y is dependent, x is independent, right? So y depends on x. So we're just trying to study the possible values of x here. So it's just one dimensional. If I had a function like this, don't write this down, z equals f of xy, so I'm just freaking you out right now. That's a three-dimensional object, so you have a z-axis. So now x and y are my independent variables, and z is the dependent variable. And then I ask you to find the domain of that. So for example, don't write this down, but let's say we have, I don't know, something like 1 over x squared plus y squared. Whatever that is, right? I mean, we don't need to understand what the shape of this graph is. We can totally graph it. It should be fun. Want to try it? Let's see if I can. I'm geeking out right now. What? I don't know. Well, you want to draw it? You want me to draw it by hand? I don't want to do it by hand. 3D graphing. I mean, the three-dimensional graphs are quite fun. Can I mess with it? Oh, see, I want to be able to rotate them. Oh, foo-plot. I can do 3D plotter? Where is the 3D plotter option? What? I didn't know. I like foo-plot. We used foo-plot a lot, right? Where's the 3D? It said 3D. Oh, polar, parametric. Nope. What? Switch towards. No. I'm sure we'll find something. Here we go. Here's 1 divided. So this is just x squared, y squared, just parabolas all around, so you get a bowl. Well, I'm going to invert it. So it's going to be like this. So it's going to have like a little bump. It's kind of basically you drop a rock in the water and that goes like that. This is my prediction. And it will have a hole in the middle. Well, close enough, I guess. Yeah, you're right. What? Well, I went 1 over. So, because you see, as you get closer to 0, the things get infinite from each direction. So you actually, it's undefined at the origin, right? You cannot have 0, 0 for the, right? The point 0, 0 right now. So the domain here will be all ordered pairs xy, so that xy does not equal to 0, 0, right? But if I try to graph this will be a two-dimensional. Basically, I'm just trying to answer this question. I mean, if I try to graph it, it's an entire plane except for one point. So everything else I can use in this function except for the origin. So that will be a two-dimensional graph because my domain is now two-dimensional. In the functions that we're dealing in pre-calc, and you'll deal in calc 1 and calc 2, your domain is one-dimensional. In calc 3, you're going to have two-dimensional domain. What? Yeah, calc 3 is you study functions of 3 dimensions. All right, anywho. So we have to be careful with the square roots. We have to be careful with division. Here's another example. F of x equals x over x squared minus 9. Do you know how to deal with this friendly function? How to find a domain of something with the denominator? What do I need to make sure? Yeah, so denominator does not equal 0. So a good thing is always to factor these things, right? X minus 3, x plus 3. So then it's obvious x cannot equal positive 3, x cannot equal negative 3. So the domain here will be all x's such that x cannot equal plus or minus 3 using the set notation. So this is set notation. The interval notation, you still have the entire number line with just 2 points removed. So it is everything from negative infinity to negative 3, union from negative 3 to positive 3, union from 3 to infinity. Right? Do you remember how to sketch one of those things? Sketch a graph of that function? I mean, not just, well, yeah, the graph of the solution will just be, you'll remove negative 3 and you'll remove 3, so it's like that. That's the graph. But the graph of a function, if you ask to graph this whole thing, remember how to do that? We did that in algebra, chapter 4, graphing rational functions, right? What is the what is the x-intercept here? Three is not even on the function. We cannot have 3. What is the x-intercept? How do we find x-intercepts of functions? Anyone? Yeah, that your teacher did go over it. I know, I'm sure your teacher did go over that. You just didn't pay attention. What? Yeah, something with the numerator. When, because you know, x-intercepts, those are the zeros of the function. We talked about that, right? So basically, whatever makes the function equal 0. Now, function is a fraction. When can a fraction equal 0? When the numerator is 0. When is that numerator 0? 0. So that happens to be both x and y intercepts, right? Now, what are the vertical asymptotes here? Negative 3 and 3, so we have negative 3 here, so here's a vertical asymptote, and here's positive 3, so here's another vertical asymptote, right? What about horizontal asymptote? Is there one? What? Yeah, there is one. What is it? Oh, that's an asymptote. Did your teacher go over that? Yeah, these are the invisible lines that your function kind of get close to, but doesn't really touch it. Yeah. So how do we do that? We have 3 cases. Degree of the numerator is less than degree of the denominator, degree of the numerator is the same as the degree of the denominator, or degree of the numerator is greater than degree of the denominator. Each one of those cases produces different asymptotes. So we have degree of the numerator is less, right? So it's small divided by big. What happens when you divide small by big? What does it tend to become? Small values divided by really big values. Small. Now, how small? Smaller. You can make it as close to 0 as you like, right? So your horizontal asymptote is the x-axis. So now, these are the harder cases, by the way, when your horizontal asymptote is the x-axis. So all we need to do is to pick one point. Pick something, let's pick something over here. What's over here? 30. Let's plug 30 in for x. 30 divided by 30 squared minus 9. Is that going to be a positive or a negative number? Positive. So the graph of the line is above the x-axis there, right? So therefore, the only way to go is this, right? Now remember, I know your teacher didn't tell you that, because this is, I told you guys, how the things alternate at odd multiplicities. So if it's positive on one end, and the multiplicity of that asymptote is 1, then the sign has to change. So it will start below, it will go through 0, and will go above. So odd multiplicities, the sign always changes from plus to minus, from minus to plus, from plus back to minus. That's the graph of that function. Your teacher probably told you pick points on each interval, and you'll get same thing. But this is quicker. Interpret the multiplicity. Multiplicity is your friend. All right. Here's another example. F of x equals x squared minus 4 over x minus 2. What is the domain of this function? Very good. All reals such that x does not equal positive 2. Although this function simplifies, right? If I go ahead and simplify this function, I can factor the numerator, and one of the x minus 2 cancels, and we get x plus 2 in the end. That does not change the fact that the domain of this function is all reals except for positive 2. Okay? All it does, it punctures a hole in the graph of that function. Because what is the graph of this function? What was that? Yeah, it's a basic line. The y-intercept is 2, the slope is 1, so it starts at 2 and goes over 1, up 1, so you get yourself a graph, right? But when x equals 2, there's actually a hole in the graph. So you just you're showing that there is no value here. So that's the graph of that function. So sometimes if you have a graph and you want to put a hole in it at a certain value x, you put the same factor in the numerator and in the denominator. So it just changes the domain without affecting the general shape of the function. Okay? So like, for example, if you have, I don't know, you have an upside down parabola, right? Let's say the vertex is, what does it look like? 3, 4, right? Then we know, this is a new example, then we know the graph of this function, I mean the function is x minus 3 squared plus 4, right? That's how we go, that's how the vertex affects the actual equation, right? You agree with that? Now let's say if I want to expand this, this is x squared minus 6x plus 9 plus 4, so the function is x squared minus 6x plus 13, right? That will be the function of that graph, right? But let's say for whatever reason, you made an experiment and when x equaled 4, you didn't get any function value, something exploded or whatever, there's no data point there. So in order for you to actually fix this function to represent the whole at x equals 4, you'll just, so here's a new function, you'll go x squared minus 6x plus 3, but then you multiply it by x minus 4, and you'll divide it by x minus 4. So that cancels, right? Oh, 13, yeah. Yeah. It's just, I'm allowed to make those errors. But yeah, you're right. But does that make sense? So I'm putting the same fraction in the numerator and denominator, so the ratio is 1, so I'm not affecting the shape of the graph, but all I did, I affected the domain, because now I have a denominator. That's, I have to be careful. So that's how you put a hole in the graph. And you can put as many holes as you like. You just keep adding the factors. Fun stuff? Okay. Did my thing just die again? Okay, no. I like this whole lecture notes on saving paper. I know. Like this is a canvas from last year, it's just, and apparently if I look at the canvas pages, it works a lot smoother than if I download the PDF file, then I look at the PDF for whatever reason. PDF is not very, cannot move it as easy as Canvas, so it's actually better. So it's pretty cool, yeah. And then of course I can cheat, I can start Googling stuff. So g of t is 4 over 6 minus the square root of t plus 3. Oh, this is a fun one. Yeah. So this function contains two problems. In addition to division, there is a square root in it. So I have to satisfy both. I have to make sure, one, the square root is happy, and two, the denominator is happy. So first, let's make square root happy. So happy square root. So I'm going to take the radicand, set it greater than or equal to 0, solve that. So t plus 3 has to be greater than or equal to 0, right? So that means t is greater than or equal to negative 3. So boom, we restricted the domain already, right? Well, now I need to go back and solve the denominator, the entire denominator, make sure that it's not 0, right? So making the denominator happy. So I'm going to take the denominator and set it to, well, equal 0, and then solve it, and then make sure to exclude that number, right? Basic. So how do I solve that equation? I can go totally. How would you like to go? Okay, or add square root. How about that? Same thing. This way you'll just have, you'll just have pluses everywhere. It's exactly the same thing as you said. Is that okay? Totally. Now what? Square both sides. So we get 36 equals t plus 3. So t equals 33. Remember, when you square both sides, you kind of want to check. Remember that? Sometimes you get extraneous solutions when you square both sides. So, but it works. 33 plus 3 is 36. Square root of 36 is 6. Boom, done, right? Because if it was, just a quick note, if this was 6 plus the square root, and we've done the same thing, we would come up to equals 33 again. But you go back, it doesn't work. So t equals 33. So that means that t cannot equals 33, right? So, but right now, my domain was everything from negative 3 to infinity, right? But then 33 cannot be part of it, so I have to find 33 and punch a hole at 33. Just remove one more point. So the complete domain would be, I can use the interval notation, everything from negative 3 to 33, parenthesis, union 33 to infinity. Right? Okay. So this is as far as the domain is concerned. And again, this is our little algebra review. It's part of the course. So you guys feeling pretty good. How many people were missing? We're missing Anna and well, I don't think we'll see Bradley anymore. And then, what? And those other two, I don't know. Were they in our class or were they in our class? You were in different classes. You were in the evening class, you were in the morning class. Well, morning for some of yous. Some of yous. So, difference quotient. Do you guys remember that friendly animal from algebra? The whole f of x plus h minus f of x over h. Yeah, you remember that thing? It's going to be a big part of your Calc 1 life. Again, this represents, from a algebraic point of view, this represents a slope of a line. Okay? And if I start graphing things, again, don't write this down, derivation of it, but the idea is, if I have a function, whatever this function is, and I have a point on a function, let's call that point x, then the y value of that point is f of x, right? So the coordinates of this point would be x, f of x, right? Just using all the notation we understand. And what I want to do, I want to find the slope of so-called tangent line, meaning a line that touches the graph at just one point. Okay? So, can you find the slope of a line knowing one point? No. Because how do you find the slope of a line? 2 points, changing y over changing x. So I have no reference. I don't have another point. So what we agreed on, we'll say, well, let's take another arbitrary point on the line, on the graph. Let's say that point is h units away from x, so therefore this value is x plus h. Okay, so we're actually labeling the distance from original x value and the, I'm going to cheat a little bit, I need more over y-axis. So then the y value is f of x plus h. All right, so the coordinates of that point would be x plus h and then f of x plus h. So instead of finding the slope of the tangent line, I will find the slope of this line that's called a secant line, the line that goes through few points through a graph. Okay? So is the slope of a secant line going to be the same as the slope of this tangent line, just by the way the graph appears? Say no. Okay, good, right? They're different. But the way we can make them closer, because that h was arbitrary, right? I can keep making this h smaller and smaller and smaller and smaller. So basically, I'm moving this point closer and closer and closer to the original x, right? Like I said, let h equals 1, let h equals 1/2, let h equals 1/10, let h equals 1 over a million. And basically, h is virtually 0. So as we shrink that distance, the secant line slowly becomes a tangent line. So when I say as we shrink that distance, I'm already talking kind of calculus-y type of terminology. That's what we do in calculus. Right, but what we say, it approaches the tangent line. So we'll see a bunch of values that get closer and closer and closer to something. Let's say the true slope is, for example, 3. The slope of a tangent line is 3. But I keep computing the secant lines, and I'm getting 2, 2.5, 2.6, 2.9, 2.99, 2.9999, 2.79. So I'm like, all right, so what we're going to say in calculus, the limiting value is 3. So everything approaches 3. So this is why, okay, I'm not going to say this is why what, but that's the logic there. So we don't need to worry about making h small in this class yet. We just need to make sure we understand how to set things up, just like we did in algebra. Okay, but the logic there is, this is where the formula comes from. And the whole idea of a tangent line, the secant line, the slope of a secant line tells us the average rate of change in our function on this interval. It just takes change in y divided by change in x. That's the average change. And when you were in algebra, you were told that interpretation of a slope is the rate of change. Your hourly pay rate, that's the rate of change in your paycheck on average, right? Whatever bucks an hour, right? You driving down the street 60 miles an hour, well, bigger street, and that's the average rate of change of your position, right, versus time. Now the slope of a tangent line is it's no longer an average rate of change of an interval, it's a instantaneous rate of change at that instant, at that point. So when you get that speeding ticket, it has nothing to do with your average speed. It's like how fast you were going at the instant when you got shot with one of those radar gunny things, right? So that's the difference between the average rate of change. You say, I drove from here to Denver in 3 hours. So on average, you were going 60 miles an hour, for example, roughly, right? Yeah, what is it? It's 160 miles, right? DIA is 180 miles. So if you go from here to DIA in 3 hours, that's 60 miles an hour on average, right? 180 divided by 3, right? On average. That means you stopped for coffee, you went around a couple of deers, but on average, I'm not saying you were going 60 miles an hour all the time. That's impossible. But on average, you went 60 miles an hour. But then on some of those, between Kremlin and that other thing, you got a speeding ticket on those straight lines because you were going like 90. So, and that has nothing to do with the average speed. That's how fast you were going at that instant. No, the slope of a tangent line at the specific point stays the same. If I change the point of tangency, then the slope changes. But if I have a fixed function with a fixed point, the tangent line, the slope of the tangent line is fixed. It's unique. It doesn't change. Okay? So, yeah, so if you move to another point, that it will change. I don't know what you're talking about. Well, yeah, I mean, if I start tilting it, then yeah, it might connect more than one point on the graph. Is that what you're asking? Okay, I'm not sure what you're asking. Not a big deal. But anyways, this is why in calculus we study change. So the whole deal between average, we can do average in algebra. We cannot do instantaneous in algebra, but we can do it in calculus. Now, again, but I think some of you heard the story how you can still get a speeding ticket for average rate of change. Did I tell that story? Because usually, by the way, every speeding ticket you get, in reality, is your average rate of change. Because it's very hard to measure. How do you think they measure your, how do they measure your speed? Yeah, but you see, but think about this. If I do that, I see one car standing and one car driving at me. And let's say at the point when they're the same distance from me, I hit them with the laser gun, or whatever, I'll get the same information. I'll get, okay, that's how far they are from me. So that's why I have to do it twice. Because they'll say, okay, I hit it twice, and it took like that instant of a second, and the distance changed. So I say, okay, it took like 1/10 of a second to cover that much of a distance, so therefore I know how fast you were going on that little interval. While the car is parked, I go bam, bam, distance stayed the same, so okay, zero speed. So they actually do average rate of change in a very small interval. The helicopter thing, because that's complete, they cannot do laser because everything is moving. You know how the helicopter does it? Yeah. Sometimes you're driving on the highway, there's like a white line, and then they're like 100 feet or whatever, or 1,000 feet ahead, there's another white line. So there's literally a dude with a stopwatch go click, click. So you drove those 1,000 miles, between the two clicks. So they have a chart. So like on average, you drove, 90 miles an hour on that interval. So they send you a speeding ticket. No. Yeah, but then the whole, yeah. So if you enter the, every time you cross a white line, you just like pull over, like stretch and then get back and then bolt it again. Because then on average, it took you an hour. So you heard my New Hampshire story, have you? That was like years ago. I used to go to school in Maine, and like my family lived in Jersey. So I had to do that I-95 crap a lot. And if you go on the East Coast from from Jersey to Maine, I don't know if you're doing that, you kind of cross New Hampshire, and there's like a little tiny part of New Hampshire. And you can literally drive through New Hampshire in like under 10 minutes. And of course, everybody's like, hey, how long it took you to get through New Hampshire? Like, oh, 6 minutes. Oh, awesome. But the way you do New Hampshire, you enter New Hampshire, and you get one of those, you go through the toll booth, you get one of those tickets that says, exit 1, like $1, exit 2, $1.25, and so forth. And then when you exit New Hampshire, you give them a ticket and you pay the thing. And sometimes, well, here's your change and here's your speeding ticket. Because the time when you get that little ticket, the time is printed on it. And when you give them the ticket, they're also aware of time. Like, all right, so it took you 6 minutes to drive whatever miles in New Hampshire. So on average, you were going 90 miles an hour. And there's a theorem in math that says if on average you were going 90 miles an hour, then there is at least one moment when you were going exactly 90 miles an hour. You cannot claim that, I never went above 60, while my average is 90. You might have gone 60, then you went like 120 or whatever. But as you were speeding up from 60 to 120, you crossed the threshold of 90 miles an hour. So you get a speeding ticket for your average speed. They cannot assume that you might have gone faster at some points, because you might have just gone 90 miles an hour on cruise control. Okay? Same thing, now it's with when you go to DIA on 470, when you're late for your flight. So you just kind of bolt it, and you don't even have to like pull over to pay your toll. They just take snapshots of you. So they totally measure the average velocity. They know how fast you go from one, toll to another toll, because they take picture of your license plate. Like, oh, it took you 12 seconds to go from here to here, so you're going like 300 miles an hour. So you get technically, you should be able to get, the ticket for the toll, because, right, they just mail it to you now, plus the speeding ticket, because, on average you went 100 miles an hour, so boom. I don't know. I'm teaching math here. But I'm just showing you the difference. So they do that too. Yeah, they will. Don't worry. Maybe. Yeah, whatever the license plate is registered at. Anyways, so let's do some examples. Some examples, we have f of x is negative x squared plus 3x plus 4. So we want to set up and simplify the difference quotient. So the setup, again, it's f of x plus h minus f of x over h. So we just use the function notation. We'll just say, okay, f of x plus h is negative of x plus h squared plus 3 times x plus h plus 4. This is f of x plus h. minus the original function. Put your original function in parentheses to make sure you actually subtracting it, because the negative distributes through everything, all over h. Does the setup make sense? Now, if you go back to the whole story, how h is small, h is virtually 0, so now we're in a big problem, right? H cannot really be 0, because it's division by 0 type of deal. So this is why when I'm doing algebra, I was always telling you, you simplify it until you cancel that original h. Because when that original h disappears, then it's like then you can say, well, let h be 0 then, and everything works out. So, well, now let's do some algebra. So it's minus squaring the sum x squared plus 2xh plus h squared. Distribute 3, so plus 3x plus 3h plus 4. And then distribute the negative, so it's plus x squared minus 3x minus 4, all divided by h. Right? I'm still going to distribute the other negative. But right away, I can kill 3x, 4, 3x, 4. Those are gone. Right? So I'm going to distribute the negative. So we'll get negative x squared minus 2xh minus h squared plus 3h plus x squared all over h. So the squares cancel. Negative x squared, positive x squared. At least every term in the numerator has at least one h in it, so I can factor it out and reduce. So this will allow me to actually, okay, not negative h. This will allow me to study, to find the slopes of tangent lines, because I'll just ignore h from then on. H is negative 2x minus h plus 3 over h, so h is canceled, and we'll have negative 2x minus h plus 3. Does that make sense? This is how far we've gone in algebra. This is how far we go in pre-calc. Do you want to know what you do in calculus from now on? This is the difference between algebra and calculus. And please don't laugh at this. But in calculus, you do the following. Let h be 0. All right, that's my answer now. I just did calculus. Yeah. So now, for every x, if I plug in every x, right, I can do anything. X equals 12, x equals negative 7. The answers will be the slopes of tangent line to the curve of that graph at any given x. H no matter anymore, because I made it 0, because it's as small as possible. So then, yeah, so basically I'm finding the slope with just one point. X equals 10, plug in 10, negative 20 plus 3 is negative 17. So slope of a tangent line when x equals 10 is negative 17. So the function changes at the rate of negative 17 per unit at that instant. And you move it forward, or you go back. How about 0? You plug in 0, you get 3. So the slope of a tangent line when x equals 0 is positive 3. Isn't that cool? So I just did calculus. No, you give a point that gives you the whole slope. So this is the function that outputs slopes. No, I no longer do. That's the whole point of that. The h was providing that second point. But then I made h very, very small, virtually 0. So I can just ignore that. Right? Because in this equation, if h is small, if h is like 1 over a billion, like who cares? It does not change. You know, my answer is negative 17. Bunch of zeros 1 then. Well, who cares? It's just negative 17. Yeah? That's literally the difference between algebra and calculus. You're allowed to just erase the h. Calculus is easy if you can do algebra. Very true story. Okay, let's do another one. Okay, this is a fun one. F of x equals 3 over 2x plus 1. So we always like to do the rational functions, but again, I want to find difference quotient. So we'll do f of x plus h minus f of x over h. So when you set this up, you'll get 3 over 2 times x plus h plus 1 minus 3 over 2x plus 1 all over h. Right? The first one is x plus h, f of x plus h, followed by f of x divided by h. So here's what we call a complex fraction. The easiest way to do that is to clear out all the little denominators. So we look at each term individually, and we find the LCD for all of them. So the LCD is the first denominator times the second denominator Well, the h does not have a denominator, right? H is, if you just look at h individually, it's just h over 1, so it does not contribute to the LCD. So the trick is to multiply and divide by that LCD. So when you multiply, your denominators just multiply straight up. There's nothing fancy happens. The denominator is h times 2x plus h plus 1 2x plus 1. Right? Just multiplying straight up. But in the numerator, something fun happens. You take this whole thing and you multiply it by the first fraction. So the big denominator cancels with 2x plus h plus 1, and we're just left with a 3, and the second part of it, 3 times 2x plus 1. So this is what we have, 3 times 2x plus 1, minus, we do this product again. Now 2x plus 1 cancel, and we're left with 3 times 2 times x plus h plus 1, like that. So we don't have any messy denominators. Now we can just simplify until it all goes away. Now keep in mind, we're after this. This is what we want to cancel. That's what's causing trouble right now. Because remember, I want that to be 0. It's not right now. So the rest is just algebra, you know, whatever. Open up the parentheses, combine like terms. Don't mess with the denominator. Leave it alone. So it's distribute 3, so it's 6x plus 3 minus 3 times, let's simplify that one, distribute 2, so 2x plus 2h plus 1 over whatever the denominator is. You can totally just write it like that because it doesn't matter at this point, you know, because we're just messing with the numerator. So let's keep messing. It's 6x plus 3 minus 6x minus 6h minus 3 over the denominator. Right? 6,633. They cancel. So we're left with negative h, negative 6h, negative 6h over, I'm going to write the denominator now, h times 2 times x plus h plus 1, 2x plus 1. So I can cancel those two. And I'm done. I killed the original h in the denominator, right? So the answer is negative 6 over 2 times x plus h plus 1 times 2x plus 1. Is that okay? This is the answer in algebra. This is the answer in pre-calc. So we're done. When you're in calculus, and this is the fun part. This is where I get to have fun. You stand, look at this, you go, let h be 0. So you just, well, okay, let h be 0. Doesn't cause any more trouble. So then the answer is, look, it's now you're left with just 2x plus 1, 2x plus 1, right? So in calculus, it's negative 6 over 2x plus 1 squared. You just get rid of h. So now, for any value of x, you get the value of the slope. So you get a new function that outputs slopes of the tangent line, provided just one point, which is kind of a cool idea. But anyways, for now we just plus h. But yeah, so calculus is kind of easy. And then there are also shortcuts. So you will not have to do the difference quotient at some point. You can just, there is a pattern. You'll recognize a pattern, and then it's really going to go down smoothly. All right. Questions on this? All right, so I'm going to talk a little bit about graphs. So we do have some basic shapes. So you have your parabolas. So it's y equals x squared. You have your cubics, y equals x cubed. You have your square roots, y equals square root of, not 3, I don't know why I wrote 3, because I saw 3 here, and my brain went to 3. Now I need x. Your absolute values, your reciprocals, your linear, you know those general shapes. Now you also know from algebra, you know exponential and logarithmic shapes. So in general, the exponential graph is this. This is where an a is greater than 1, right? So it's a growth function, and then you have your logarithmics. Yeah. Oh, that's a good point. I said reciprocal, but I didn't write it, so it's 1 over x. So reciprocal function. Oh, sit down fast. Some of these functions have symmetry, don't they? Do you recognize the symmetry in some of these functions? The first function, does that have any type of symmetry? Yeah, what kind of symmetry? Y-axis. What do we call those functions that symmetric around y-axis? What? Great? No. Well, they're awesome for sure, but we call those even functions. The function that's symmetric with respect to the y-axis are called even functions. So it doesn't matter whether x is positive or negative, the y value stays the same. So this is the idea behind this graph. It doesn't matter whether you put negative a or positive a. In both cases, you get the same value of a squared. So that's an even function. So do you see any other even functions on this list? 4, right? The absolute value. That's another one. But the definition of an even function, so symmetry, even functions, basically they satisfy this. F of negative x equals f of x. So it doesn't matter whether x is positive or negative, the function values stay the same, and the symmetry is the y-axis. Is y-axis. Again, in algebra, we kind of use symmetry to sketch quicker. If you know in advance that your graph is symmetric, so you only really need to sketch half of it, and then the rest is taken by symmetry. In calculus, you're actually going to benefit even more from it when you realize the function is symmetric around the y-axis or whatever. So that's the definition of an even function. If I go back, there's another type of symmetry, like on the cubic one, that every point on the graph, if you rotate it 180 degrees, you get another point on the graph. Yeah, so it's about the origin. So that means here you have x, y, and here you have negative x, negative y. So basically, if you change the sign of the x, it will change the sign of the y as well. So we call those odd functions. Symmetric around the origin. Do you see any other functions that are symmetric around the origin? 5. This one is also, if you rotate one around the origin, you'll get the other one. So we call those odd functions. Basically, if f of negative x equals negative f of x, that's the definition. So if you change the sign of x, it will change the sign of y as well. The symmetry is the origin. How's that? Do you remember that from algebra? Technically today, but I don't know. We don't have much going on. What are you in the middle of the class? Now I don't know what I was talking about. So the way you test, given a function, the way you test whether it's odd or even, you start in the same place. You go f of negative x, and then you do the math. And if all negatives disappear, then you got yourself an even function. If you're able to factor out the negative, then you got yourself an odd function. I don't know. I don't want to do any examples of that. Okay. Because I'm just kind of flying through some of the graphing things. Now, transformations. Remember in algebra we studied 10 total transformations. You go up, down, that's 2, left, right, that's 4, flip over the x, flip over the y, that's 6. You stretch horizontally, you shrink horizontally, that's 8. You stretch vertically, you shrink vertically, that's 10, right? So let's call it acrobatics of functions. I'm just inventing those terms. So we're just going to mess with it, right? So, and I'm just going to really quickly remind you, I'm not going to go into the depth that we usually go in algebra, but so let C be a positive number, okay? And the graph y equals f of x is known. So either it's one of the graphs that I already drew, or, you know, they give you here's the graph. So then, in order to sketch the following, so if you take an original function and you add a number to it, where is the graph going to go? If you add to the function, you're just conducting an orchestra right now. Well, is it up or down? We're adding a positive number. Up. So we're going to move up. Okay. If I go y equals f of x minus c, what will happen? Down. Up c units or down c units, right? Now, if I do y equals f of x plus c on the inside, where do I go? Left. And for, if I do f of x minus c, we'll move right. Now, for those of you who were in my algebra class last semester, I told you a pattern about this, right? There is a grander pattern. And I think I noticed that pattern when I was teaching this class last semester, and I got all kinds of proud of myself. This is an awesome pattern, and then I shared it with you. It's not in the book. So here's the pattern that we've noticed, and I've shared. I don't know if you remember the pattern. Do you guys remember the pattern last semester? No? Because, okay, so we can group all these transformations. I mean, we can split them into two groups. You're either messing with the independent variable, or you're messing with dependent variable. You're either messing with the x, or you're messing with the y. Now, 1, 2, or 3, 4. 1, 2, am I messing with the x or with the y? Y, right? I'm adding something to the whole function. I'm messing with the y. While 3 and 4, I'm actually on the inside messing with the x, right? So here's the pattern. If you're messing with the y, all changes happen across the y-axis. All changes are going to be vertical, and they will be very intuitive. They'll be exactly what you expect them to be. You add a number, everything goes up. You multiply by a big number, everything goes up. You subtract a number, everything goes down. You multiply by a small number, everything decreases. Everything is intuitive, makes us happy. Less than 1, yes. So, you know, if your function was 2, you multiply by half, it becomes 1. So everything is intuitive. Now, when you're messing on the inside, when you're messing with the x, all changes happen across the x-axis. All changes are horizontal, and they're counterintuitive. If you add a number, you move left. If you subtract a number, you move right. If you multiply by bigger than 1, everything actually shrinks. And if you multiply by a number less than 1, everything stretches. So it's opposite of what your common sense suggests. Isn't that nice? And it works. It's totally true. Except for the reflections. The reflections, you have to remember that. Well, the reflections, they just make sense without the opposite. Because here are the reflections. If you do y equals negative f, are you messing with the y values or with the x values? Y. So change happens along the y-axis. So you flip. You flip vertically, so you flip over the x-axis, right? Your y values change. Positive become negative, negative become positive. So he flips over the x-axis. So you're flipping. So here's the x-axis. You just flipping over the x-axis. That's my notation. Flipping over the x. While this thing, you are messing with the x value, so the change happens horizontal. So positive x becomes negative, and a negative x becomes positive. So what I'm miming here is that I'm flipping over the y-axis. So if this is the y-axis, it flips like that. So the graph just reflects. What? Actually, I don't think so. I'm just realizing I'm flipping it 360, so this is back where I started. Right? I should just kind of make it just stop here or kind of stop there, maybe. But you get the point, right? Now the other two, I'm going to say let c be greater than 1. So then 7 y equals c times f of x. So I'm multiplying the y values by a number bigger than 1, so everything will happen as expected. Things will grow. So we'll stretch. How can I? So I don't. Well, let's come up with a symbol for stretch vertically. I think I have an idea. It's a good one. I had a different one in mind. Yeah, I like that. It's like this, right? So then let me erase this thing so it doesn't confuse anybody. So then we'll just stretch vertically. Is that what you're saying?
Well, yeah,
I like that. Yeah. Let's see what else I can do. I had another idea. I don't know if I can do that. Let me just have fun with this for a minute. Yeah. No, it just stretches. It just stretches all across. I just want it to kind of go boom. I can probably do like that, right? Stretches. Circle becomes stretches. Anyways, yeah, I like Arthur's idea better. It just so it stretches vertically, and if c is still positive but less than 1, then again we're messing with the y values. Things will shrink. So just as expected, if you try to do cf of x, so shrink, things will, how would you do that? Like that? Shrink? So this is stretch. Okay, I'll write this. Stretch, shrink. But it gives you a direction. So this is the pattern that I was telling you about. Messing with the y, everything is vertical, and everything what you expect it to be. Bigger than 1, things get bigger. Less than 1, things get smaller. And 9, again, let c be greater than 1. Then if you want to do y equals f of cx, so you're multiplying the x, you're messing horizontally, so things are counterintuitive. If you multiply by bigger than 1, but things will actually shrink horizontally. Things will get smaller, tighter. While if c is less than 1, but bigger than 0, still positive. We know what happens when they're negative. We already talked about that. So things will stretch in the horizontal direction. Okay? So when we were in algebra, we weren't really able to appreciate the stretches because all our functions were just kind of, okay, you take a parabola and you stretch it, it's just a parabola. You need a point of reference to show how it changed. Stretching a parabola vertically, same as shrinking a parabola horizontally. So that's another weird thing. But in this class, when we actually get to trigonometry, you know, our graphs, you know, going to look like that. It's fun to shrink and stretch and do all that with them, because we can model a whole bunch of harmonic behaviors, your heartbeat. And you can increase your heartbeat by just changing a little constant in your heart function. And it increases, or you can slow it down, but you know, we can play gods with math. We can build a little dude and have a function of a heart. And, you know, does that make sense? Kind of. But remember this pattern. It's a cool pattern. I should patent that pattern. I've never heard it before though, so I independently discovered it. Well, you know, I'm already getting money. So, okay, this is messy. Now this is confusing. I need to get rid of this sign. So here we go. I'll get rid of that too. Otherwise, it's too many errors. So yeah, if you mess with the y, things change along the vertical axis and as expected. If you mess with the x, things change along the horizontal axis, kind of opposite of what you expect. All right? Okay, good. I'm done.